Okay, let's get started. Good evening and welcome to the week 9 live session. So, let's start with some of the doubts that people had asked last week and then we'll move to this week's recap and questions. So, I think a couple of people last week mentioned that they did not understand thread coarsening very well. So, we'll talk about what is thread coarsening for a bit. Yeah. So, the idea of thread coarsening is that you merge multiple threads into one, and again, there are various benefits that come out of this. For instance, you avoid redundant memory calculations, memory accesses, and calculations. So, in essence, it's very similar to loop unrolling, but it's applied across parallel threads rather than loop iterations. And like I said, there are a lot of beneficial effects, and you basically require lesser number of threads. For instance, let's say we had 4 threads and now I'm coarsening it by a factor of 2, meaning I'm merging the work of these 2 threads into one thread, and therefore you'll be launching only 2 threads. And again, increased number of instructions increases scope for exploiting hardware level parallelism as well. What are the disadvantages of doing this? Basically, your resource consumption like registers go up, and that could reduce your total occupancy in the SM. So occupancy is defined as ratio of active threads per SM and max number of active threads per SM. So even though an SM may have a limit like say 1024, you may not be able to retain that many actively because of the increased resource consumption, right? So you have some effects like that. This is a very simple example where, for instance, you have the without coarsening here, where everything deals with just one element, so to say. And here you have the work of 2 threads being done in one. So this is a coarsening factor of 2. So again, coming to the coarsening factor and its definition, it is a number of times the body of the thread is replicated, and it needs to be chosen depending on the program and the hardware. So you can decide it through some kind of static analysis of the program that you do by looking at the logic and figuring out what might be better. You may also need to, in most cases, it's practically done through profiling. You may try out something, see what happens to various parameters, and depending on what your profiling tells you, you may change this. So again, we have 2 types of coarsening. The examples that I gave you before were all thread level coarsening. You could also do block level coarsening. So you could have one block kind of do the work of multiple. Like we said, thread coarsening applies coarsening at the level of individual threads. You combine 2 or more threads. How many you combine depends on the coarsening factor. So each thread performs the same amount of work but with fewer threads. Again, there are limitations in terms of register, shared memory, and so on. These hardware constraints limit how much you can coarsen. Then I think this was also something somebody asked. Stride length was something that was confusing. So when I say coarsening factor of 2, I mean that you're basically going to, in the thread level coarsening idea, you're basically going to club the work of these 2 threads, and the new coarsened thread will be doing the work of these 2 threads. But which threads do you combine is what is decided by the stride length. Basically the offset between the thread IDs that are going to be combined. So again, you have a lower bound and an upper bound here. So the minimum or the lower bound is the warp size. Again, why is this done? So that your memory accesses from a warp are still going to be coalesced even after the coarsening. And the upper bound, or the max stride length, is basically number of threads per block in the dimension of coarsening divided by coarsening factor. I think we saw an example last week where I showed you why this had to be there. And if not, you will basically not be able to combine all the threads in a block properly, right? So this is the upper bound on the coarsening factor. So that's about thread level coarsening. Now coming to block level coarsening, you are combining the work of several thread blocks into one block. Number of threads per block still remains the same, so the number of executed thread blocks is reduced. So basically every block handles an increased workload, and again you have increasing resource requirements in terms of register, shared memory usage, etc. Again here you have the same notion of stride length, except that now it is an offset between the block IDs that are to be merged. Again, the min stride length here, remember that there we were concerned about the memory access pattern, but here there is no influence of this factor on memory coalescing, because the access patterns within a block are not going to change, right? So your lower bound is simply 1. You could start anywhere from coarsening blocks that are next to each other. You could go all the way up to the max stride length, which is calculated the same way as before. Number of blocks where coarsening is applied divided by coarsening factor. Yeah, this was another question that was asked. So there are various reductions that were discussed in the lectures. So what are some advantages of first add during load? Is it only that half the values are loaded in shared memory? Yes, one of the facts is that the half the values are loaded, and the allocation process itself performs the first reduction. But there are other advantages also. The number of blocks is halved, and all your threads become busy in the first step itself, unlike the previous reductions. And your single load is now replaced by 2 loads. So all of these are advantages of first add during load. Okay, I think that was all the doubts that I had from the last week. So before we move forward, any other doubts from week 1 to week 8? Today's will be a very simple session because it's an introduction to OpenCL. So we'll go through some of the terminology and various things that are introduced in this week. And then the questions will be largely based on the terminology. So it'll be fairly easy. It's also a long weekend, so I think a lot of people may be traveling or out on holiday, but that's okay. The recording is there, so people can watch it. So for people who watch this later, if you have any doubts in the live session or you want me to address something in the next live session, please post your doubt on the discussion forum. We will continue with the recap as of now. So week 9, we saw an introduction to the OpenCL runtime system, right from how did OpenCL originate, what are some of its goals, what is the language specification for OpenCL, what is the platform model, the execution model. We looked at various terminologies like command queue, context, the synchronization. Then we looked at the memory model, the programming model, and the program structure. So let's look at some of these topics in the recap, and then we'll move to the problem solving. Okay, so this is the general GPU timeline, right? In the late 90s or the 2000s, people started using GPUs to accelerate a variety of scientific applications. So we discussed this even in the beginning of the course, right? What applications are kind of suitable for GPUs and how GPUs kind of evolved from just being used for graphics workloads to various scientific workloads, right? Now, again, like we discussed, so far we have always seen CUDA, right? And remember that CUDA works only on NVIDIA GPUs. But there are various other, not only GPUs, for instance, there are other GPUs as well, for instance, things from AMD. And there may be other accelerators. So for instance, you may have heard of things like the TPU. You may have heard of a lot of custom accelerators like the Intel's Movidius, which is called a vision processing unit. So a lot of these are coming up. So the aim of OpenCL was kind of to be an open source and royalty free standard for parallel programming of heterogeneous compute. So it did not just target GPUs, but a various other processors and accelerators. For instance, it could use CPUs, it could use DSPs, it could use a lot of other things, right? And again, as a framework for parallel programming, it included a language, a standard for the language, the API, the libraries, and the runtime system. And it supported for languages including C, C++, Python, and Java. So the biggest difference between CUDA and OpenCL is this support for heterogeneous compute. So you can see today that FPGA is computed and supported, and you may be able to see a complete list of devices that are kind of supported today. And the best part is you can write the same code. If you actually tried to work with each of these, right, you would have to probably write different code for these different devices, right? And writing a single application that is using this sort of heterogeneous compute effectively is difficult, right? That is the gap that OpenCL tries to address. And the difficult part there is some of these devices may be from different vendors. So you need it to be both cross-platform and cross-vendor. So everything else is abstracted from the user, and you can kind of execute the same code on these devices, and you could balance across different heterogeneous processes. Again, remember that for instance, if I had X amount of workload, right, the GPU might be much faster than all of these others, and 80% of the work may be done by the GPU. And you may partition the work a little bit between the other three, right? And you have a lot of systems like these today that are very heterogeneous, right? Even things like your mobile phone no longer just have a CPU, right? Of course, they have a GPU and they have a lot of custom accelerators. So the better you are able to use these heterogeneous compute that's available on your devices, the better performance you could get, right? And you're using everything that's available to you. So that's the idea. Now coming to some terminology, this is kind of to connect what we have previously learned and what we are talking about now, right? So what is called in CUDA as a GPU is now referred to as a device. Again, because OpenCL not only supports GPUs but a variety of other devices. Again, things like this, multiprocessor is now called compute unit, right? Because it's more generic. These are GPU specific terms. Similarly, a scalar core is now just called a processing element. A thread is called a work item. A thread block is called a work group. And a grid is called ND range. And coming to the memory terminology, global memory remains the same. Shared memory is now local memory, and local memory is called private memory. So this is just terminology, but there may be some questions on this. Okay, now coming to the platform model. So a host is connected to one or more OpenCL devices, and an OpenCL device is a collection of one or more compute units. So you can notice this terminology being a lot more generic, right? So this is to account for the hardware heterogeneity. We no longer say GPU or SMs because you could have something else. You could have a DSP, you could have an FPGA, right? So we just talk about the host being connected to multiple devices, and each of these devices has a collection of compute units which further may be composed of processing elements. And again, processing elements could execute code as SIMD or SPMD. Now coming to the program structure and the APIs that you have. And again, you'll notice this as we discuss more and more about OpenCL. In OpenCL, you have a lot more fine-grained control as compared to CUDA, right? For instance, you will see that you can issue commands in a particular order to the command queue. A lot of things are done by using these APIs itself, right? It's not abstracted away entirely. So broadly speaking, we have the platform layer, and this is kind of an abstraction layer across all of these diverse computational resources. So you could query your compute devices. So we saw some examples like that, right? You listed all devices that were available, and then you could select and initialize the devices that are available, and you could also create contexts and work queues, right? These are your primitives. Then you have the runtime API. This is for various operations like launching your compute kernel, setting the execution configuration, managing the scheduling, the compute, and the memory resources, and synchronization. So this is broadly your division in terms of the program structure. So now we'll go a little bit into some of the terminology that was discussed. So we spoke about context, right? So what really is a context? This is created and manipulated by the host using functions from the OpenCL API. So it coordinates the mechanisms for host device interaction. It manages memory objects that are available to the device, keeps track of programs and kernels that are created for each device. The main thing to remember about the context is that it is limited to a given platform, and that helps to fully utilize a system comprising of resources from a mixture of vendors. That's about the context. Moving to the command queue. So this is mainly to coordinate executions of the kernels on the devices. It can be used to queue a set of operations, right? Basically, you have this set of commands that the host could issue, and those are queued up in this command queue. So initially, commands could be enqueued only from the host. After 2.2, both host and device side command queues allows a child kernel to be enqueued from another kernel. So you could have something that's executing on a device, queue up another kernel. To create a host or device command queue on a specific device, the API used is CL create command queue with properties, and you can set the property parameters of the command queue. Okay, with that, I think we are at the end of the recap. So before we move to the questions, any doubts so far? Some of this terminology can be very new. So if you have any questions or any doubts, we can discuss a little bit more in detail in the next session. Okay, if not, we'll move to the problems. Like I said, today's session will be shorter because again, a lot of the questions are very direct. So we'll solve maybe 4 questions, take a break, come back, and then wrap up. Okay, let's get started. What is the corresponding term in CUDA for private memory in OpenCL? Global, local, shared, private. Any answers? Okay, B, local. Yes, that's correct. So yeah, I think this is fairly clear. So we'll finish a set of these memory questions and then go back and look at the terminology. We'll move to the next one. What is the corresponding term in OpenCL for shared memory in CUDA? Global, local, shared, private. B. Yes, that's also correct. Okay, another terminology question. What is the corresponding term in OpenCL for local memory in CUDA? Global, local, shared, private. D, private. Let's take a look. Yes, that's also correct. Next question. What is the corresponding term in OpenCL for thread in CUDA? Work item, work group, compute unit, compute core. A, work item. Okay. Yes, that's also correct. What is the corresponding term in OpenCL for scalar code in CUDA? Thread, work item, compute unit, processing element. D, processing element. Yes, that's correct. So I think this is what we've had on the terminology. So let's just take a quick look at this, right? So all of this was directly discussed in the lecture. So we looked at scalar core and processing element. We looked at the three types of memory, and some of these can also be asked. So you get this sort of question, right? It's directly a terminology mapping. So it's good for you to remember what something is called in CUDA and what it maps to in OpenCL. It's a very simple type of question. Since this is introductory content on OpenCL, you will find these questions being asked. Let's see, I think that is all the terminology question that we have. Yeah, we have a few more questions. Let's take a 5 minute break and then resume. So we have around 7, 8 more questions, and some of them are numericals. So we will wrap up by, I think, 7 o'clock. So 7 or maybe 7:05 or 7:10. So it's 6:28. We'll resume at 6:33. Okay, let's continue. This is a true or false question. OpenCL context keeps track of the memory and program objects created for a given device. Is this statement true or false? A, true. Let's look at the answer. Yes, that's correct. So if you remember from the recap of the context, it manages the memory objects, keeps track of the programs and kernels that are created for each device. So both of these are true about the context. Let's move to the next question. For multiple platforms, this says devices, but I changed it because it's incorrect otherwise. For multiple platforms, a single OpenCL context can be created. Is this statement true or false? Any answers? A, true. So this is actually false. So let's go back to the definition of a context, right? So it says that limiting the context to a given platform. So let's first clarify what we mean by a platform and a device, right? For instance, a platform could be a platform you can closely associate with a vendor, right? So you can think of all devices that are from Intel to be a particular platform and so on. So if you have multiple devices from the same vendor, you can create a single OpenCL context for them. So, if this question read as just devices, then that is true. But if you have multiple platforms, as in you have different vendors and you have devices from different platforms, you cannot unify them in a single OpenCL context. So, if you have, so as of now, with platforms as the question, you cannot have a single OpenCL context across multiple platforms. You have to have multiple contexts. Therefore, this is false. Hope this is clear. We'll move to the next question. A single command queue can execute only one kernel on a single device. Is this true or false? B, false. Yes, that is correct, because you do have these multiple devices and you have parameters that you can specify in these commands that will tell it where to be executed and so on. So this command queue is not going to be only for one kernel on a single device. That is false. Host program can have access to local memory at runtime. Is this true or false? A, true. Yeah, this is actually false. So there is a memory model table that I should perhaps have put in the recap. I will put this after this question and upload the slides. So you can take a look at that to see why it does not have access to local memory. So there was a table in the lectures which said depending on the type of the memory, right? Global, local, whether the host has access to it, whether the kernel has access to it, what kind of access is allowed, and so on, right? So that will help you understand why this is false. We move to the next question. OpenCL allows synchronization across different work groups. Local memory is pointing to the memory of the GPU device. Again, it could be GPU or something else. I didn't get your question. Maybe what I can do is put in the memory access slide and then re-explain this question. That will probably help. Let me see if I can. Yeah, okay. I see your comment now. It's not memory of the CPU, it is memory of the device that we are talking about. But yeah, I'll do that anyway in the next week so that you have a clearer idea of what can be accessed where. Okay, next question. OpenCL allows synchronization across different work groups. Is this true or false? Yeah, B false. That is correct. Again, as a quick recap, we have two types of synchronization provision for in the OpenCL execution model. One is the work group synchronization, order of execution of work items in a work group. This is similar to what we have studied in CUDA. Could also have command level synchronization where you can have constraints on order of commands launched for execution, but synchronization across work groups is not supported. That's why this is false. So these with this we come to the end of the second set of questions. We have a couple of numericals which we will solve now, but this is basically another set of questions which tests your understanding on various OpenCL features, right? For instance, synchronization or the memory access and things like that. So this is not just terminology, but you have to understand what is supported, what is not supported. But these are also relatively straightforward. So we'll come to the third type of questions for today, which is the numerical questions, which may not have directly been discussed in class, but we'll see. Hopefully this will make it clear. The two input matrices for a matrix multiplication kernel implemented in OpenCL have sizes 128 into 256 and 256 into 4096. Tile size used is 3232. The target hardware can accommodate 1024 threads at max per block. Consider the following OpenCL command for kernel launch: cl nq ndrange kernel matmul 2 null global work size local work size 0 null null. what would be the suitable global work size? So you have four options here. I'll go back to the question for a minute and then come to the options. Okay, I'll move to the options now. You can take a couple of minutes. Okay, we have an answer. B, which is 128.4096.1. Yes, that is correct. It is 128.4096.1. So this is very similar to the CUDA kernel launch parameters, right? So the way you come up with your total number of threads, right? Here, for instance, you know that your output matrix is going to have 128 into 4096 elements. So your global work size would be 128.4096 and 1. I think this is also fairly easy. We have one more question in the same set. So with the same data, what would be the suitable local work size? And again, we have four options. Okay, we have an answer saying B, 102411. The answer given is 3232.1. So now looking at the hardware constraints, the maximum is 1024 threads per block. So both A and B would be suitable options. But I think why A is given as the option, it again goes back to your data dimension and how you want to kind of use this notion of threads or threads and blocks, or in this case, the work group and work items, right? So with 2D data, it kind of makes sense to have the same sort of thing in your further parallelism as well. So 3232 is what's given as the answer, 3232.1. Hope this is also clear. Let's see if we have any more questions. Yeah, I think this is the last question. So, like I said, it was a very short session, very straightforward questions. I think next week might have a little more detailed questions, since by then you'll be familiar with OpenCL. So, I think you have one more week on OpenCL, and then it goes to neural network training and inferencing, which is also a very interesting use case and application for GPUs. So, yeah, so for today, I think we'll end here. And if you have any other questions or doubts about OpenCL that's not clear and you want it to be addressed in the next live session, please feel free to ask either now or in the discussion forum, and we can take it up next week. So, we'll have 3 more live sessions for week 10, 11, 12, and a revision section at the end. So, make sure you get all your doubts cleared by then. So, yeah, that's it for today. Thank you so much for joining, and we'll see you next week.